Hello everyone, welcome to YashaswiTechHub. So we are going to cover everything which is related to Elgamal encryption algorithm. So let us begin with the introduction. The prerequisite will be Diffie-Hellman algorithm. This is a type of public key crypto system. That means it is going to use asymmetric keys. So we know that there are two types of keys, the public key and the private key. This was invented by T. Elgamal in 1985. So it is a widely used algorithm for secure data transmission, digital signatures and encryption applications. So as usual we have two users here, user A and user B. So in Elgamal encryption algorithm we are going to use three main steps. So remember the three main steps are, the first step is nothing but the key generation, the second step is the encryption, and the third step is nothing but the decryption. See, the three steps are key generation, encryption and decryption. So the key generation is going to happen in the user A side. So what user A does is, he or she is going to generate the public key and a private key set. We know that we are going to use Q, which is a prime number, and in alpha, which is a primitive root for YA generation along with this. So what we do is, we are going to have this as the private key and we are going to send the Q, alpha and YA to the public. So the thing is, this is made publicly available to the user B. How is it available? We'll be seeing in key distribution and management practices. Then when it comes to encryption, what this B does is, he is going to generate a key K. He is going to take input as the public key of A via A, and he is going to use this primitive roots and is going to generate a key K on his own. So then what he does is, he is going to generate C1 and C2. The C1 and C2 are nothing but the integers. Any communications here are converted into integers because we can easily make use of this integers and encrypt using the modular arithmetic. So basically we can make use of mathematics by using integers. So any letter is converted into the integer form and then it is done. For example, if we take the message M, which is equal to some 17, the equivalent will be nothing but the Q. So this Q will be encrypted as 17 and then it will be sent as the message in the ciphertext. This is what we need to remember. Then what happens after encryption? What he does is, he is going to send C1 and C2. So what is the help of C1 and C2? First we'll understand this C1, which is going to help A to understand what is going to be the K. He is going to send C1. So A is going to decrypt somehow and get the key K, which was generated here. And the use of C2 is nothing but the actual message. So by sending this ciphertext, the user A is going to get the key K. By using this key K, he is going to decrypt the message. This is the basic understanding of the Elgamal encryption. The numerical approach and a question will be solved now. So when you are aware of the global public elements, which is Q and alpha, what Alice is going to do is key generation. So we are going to select XA, which is the private key of Alice, which is lesser than Q minus 1. We know Q is a prime number. Then we are going to calculate YA. YA is the public key of A. We are going to calculate using this formula. So alpha to the power XA mod Q. Similar to Diffie-Hellman now? Okay. So the public key, we have Q, alpha and YA. Private key is XA. What we are going to send? The public key of A to B. So what this B is going to do is, he is going to start encrypting the messages. We know we are going to select a plain text which is nothing but M. So this M which is lesser than Q. Then we are going to generate a random integer K. By using this random integer and the public key of A, we are going to calculate the secret key K. So K is equal to YA public key of A raised to the power of random integer mod Q. Then we are going to have our first ciphertext C1 which is equal to alpha to the power small k which is nothing but the random integer mod Q, and C2 equal to the secret key into the message mod Q. So the formulas in the boxes, there's no alternative for it. So we need to remember it. So the ciphertext we have generated C1 and C2 using all these parameters, and we are going to send it to allies C1 and C2. Allies has received C1 and C2. This is the ciphertext. We know that C1 is used for calculating the key K, the secret key, and C2 which is used for finding the message. So see the formula. So K is equal to the ciphertext which is raised to the power of the private key of A. Allies is using her private key during the decryption of the key. Then we are going to get the plain text by using the C2 and this key. So we are going to find this message. So this message is decrypted over here. So we are going to see how this is connected to this formula. We are going to derive this formula using this formula. How can we do that? K is equal to YA to the power K mod Q. This will help us understand the magic behind this scheme. So we have got this formula here. What we do now is, we know that what is YA? We know that YA is equal to alpha to the power XA mod Q. So replace it here. So alpha to the power XA mod Q to the power K mod Q. So according to modular arithmetic, you need not write this every time. So it is just used for reducing it up. Okay. So K will be equal to alpha to the power XA K mod Q. Okay. So what we are going to remember is, see, alpha to the power K. What is alpha to the power K mod Q? Is nothing but C1. So go replace it with it. So alpha to the power K which is equal to C1 to the power XA mod Q. So isn't this the same formula here? Isn't this the same formula? So this is the way we are going to get this formula by using it. And similarly, let us see the relationship between C2 and this formula. See, we have C2 which is equal to Km mod Q. So what we do is multiply both sides by K inverse. So C2 into K inverse mod Q equal to K inverse into K mod, M mod Q. So we know that this is C2 K inverse mod Q equal to this K inverse and K. We know that 1 by K into K get cancelled. So M mod Q. So do not consider this mod Q unless it is a very large number. So it is just to reduce it into a smaller which must be within Q. So C2 into K inverse mod Q which is equal to M. Therefore M is equal to C2 K inverse mod Q. So this is how we have derived this formula using this one. So this is what happens in the decryption process. So the numerical on this we'll be looking in the next video. So please stay tuned. Thank you.